2 capacitors, and 1 resistor. 2 capacitors, 6 and 18 microfarads, are connected in series with a resistor and a switch. Capacitor C1 is initially charged to a voltage 120 volts, and capacitor 2 is initially uncharged. Switch S is then closed at time equals 0. What is the charge on each capacitor after equilibrium is reached? What is the new voltage across C1 after equilibrium is reached? And then what is the difference between the initial and final energy stored in the system of 2 capacitors? The current as a function of time in the resistor is presented by I equals I0 e to the minus t over tau, where I0 is 0.4 amps and tau is 1.2 times 10 to the minus 4 seconds. Find the power dissipated in the resistor as a function of time, and how much energy is dissipated in the resistor from the time t equals 0 to when equilibrium is reached. What is the charge on each capacitor after equilibrium is reached? First, we will find the total charge in the system. That will remain constant throughout the process due to the conservation of charge. Once the switch is closed, there will be a potential difference between the 2 capacitors, and current will flow, taking charge from C1, which is fully charged, over to C2, which started off with no charge. The current will stop once the potential difference on each capacitor is the same. That will then enable us to calculate the charge on each capacitor. First, find the total charge in the system. That will equal the charge on C1, because in the beginning that's where all the charge is. There's no charge on C2. That's C1 delta V1, 6 times 10 to the minus 6 farads times 120 volts, and we get 7.2 times 10 to the minus 4 coulombs. That will stay constant throughout the entire problem. When equilibrium is reached, the voltage difference across the plates here has to equal the voltage difference across here. Okay, so here is V of C1, and here is V of C2. Now notice, we didn't want to introduce another variable, which is the charge on capacitor 2, but because of the conservation of charge, we know that the charge on capacitor 2 is just the initial charge on Q1 before the switch was closed minus the final charge on Q1. So now we have a little algebra here. We multiply through. You know what? Let me get rid of these lines here. We multiply through by C1. We get this expression. Now we know C1 and C2, they were given. We put them in. And then the rest is just some more algebraic steps, and we find out that the final charge on Q1 is 1.8 times 10 to the minus 4 coulombs. Then we find Q2 final. We want to find the charge here. It's the original charge of the system minus this guy, how much charge remains on capacitor 1, and we get 5.4 times 10 to the minus 4 coulomb. Now, does this make sense? This guy here has 3 times the capacitance of C1. So it should store 3 times as much charge, and yes, it does. What is the new voltage across capacitor C1 after equilibrium is reached? Well, voltage is just charge over capacitance. We found the new charge. The capacitance stays the same, so we have 30 volts across C1. And since the potential has to be equal, we have 30 volts over here, right? So that means that no charge is flowing, we're at equilibrium. What is the difference between the initial and final energy stored in the system of 2 capacitors? So delta U will be the final energy minus the initial. So it'll be the final energy on capacitor 1 plus the final energy on capacitor 2 minus the initial energy of the system when all the charge was on capacitor 1. We substitute in 1/2 QV for all the potential energies, and then we note here what's common between the two of those guys, the final voltage. So now we can substitute in our values that we found. There's the final charge on capacitor 1, final charge on capacitor 2. Here's the new voltage, 30 volts, minus the initial energy. We get a change in potential energy of negative 3.2 times 10 to the minus 2 joules. So the final stored energy is less than the initial stored energy. Where did it go? the energy was dissipated in the resistor as thermal energy released to the environment. Find the power dissipated in the resistor as a function of time. Well, power is I delta V, or I squared R. We were given the value of I as a function of time, and we have R, so we square I. We put in our numbers for tau and R, and we get the power is 19.2 e to the minus 1.7 times 10 to the fourth t. How much energy is dissipated in the resistor from the time t equals 0 to when equilibrium is reached? Since power is equal to the energy dissipated over time, we find the total energy by integrating power over the specified time interval. Assume the equilibrium is at t equals infinity. So we have our delta E is the integral of p dt from 0 to infinity. We put in our value for power. We do the integration, okay, which is just right here. We divide through by the exponent there. And then we keep the same exponent because they're kind of easy to do integrals with. Evaluate it between 0 and infinity. And we get a negative 1.15 times 10 to the minus 3 joules. And the negative sign shows that the energy leaves the system and is transferred as thermal energy to the environment.